Welcome to this video where we present Sparse-E2VID, a model that uses event cameras data for video reconstruction. Our model takes advantage of the sparsity of event cameras to reduce the computational cost and inference time of video reconstruction. This makes our model faster and more efficient than other methods. We also train Sparse-E2VID using real noise data from an event camera. This allows our model to reconstruct video that are virtually noise-free and have high-quality outputs. Event cameras typically have a sparsity index of 90% or higher. Sparse-E2VID utilizes sparse convolution to reduce inference time and computational cost. However, it is not as easy as replacing dense convolution layers with sparse convolution layers. This is because the hidden state in the RNN module, which is a tensor that accumulates information from past events and becomes quite dense over time. Applying sparse convolution on this tensor is inefficient due to its high density index. To address this issue, Sparse-E2VID processes the events with sparse convolution in the first layers, and then switches to dense convolution in the last layer, which contains the convgru module with the hidden state tensor. Another thing to mention is that our model predicts the image gradient. This gradient is then integrated with the fast Fourier transform using the Frankit-Chalapa algorithm. In such manner, the model reduces its workload and can generate images with shorter inference time and higher quality. In this video, we compare two variants of Sparse-E2VID. The first one predicts the image directly, while the second one predicts the gradient, and then integrates it. We can clearly see the improvement in quality for the model that predicts the image gradient. While Sparse-E2VID is trained with synthesized data, we introduce real noise from an event camera into this training set. Once we finish training our model, it can reconstruct images with almost no noise. In the qualitative results, we can observe that our model is comparable to FireNet Plus at low resolutions. However, at higher resolutions, such as 720 by 1280, Sparse-E2VID is comparable to E2VID Plus, a larger model with better results. According to our profiling results, due to the use of sparse convolution, Sparse-E2VID reduces the inference time by 30% at 720 by 1280 resolution compared to the FireNet architecture. Additionally, as can be seen, the computational cost is drastically reduced by 98%. This result shows that Sparse-E2VID scales better at higher resolutions. In the following videos, we show a variant of Sparse-E2VID that was not trained with real event camera noise. This variant is compared with Sparse-E2VID that was trained with noise. In the comparison, we can see the noise reduction in the videos. We also compared Sparse-E2VID with FireNet Plus. It's important to note that FireNet has 30% more parameters and is 30% slower in inference time. In the video, we can see that FireNet Plus suffers from severe noise problems, producing almost indistinguishable images. In this video, we compare Sparse-E2VID with E2VID Plus. E2VID Plus can reconstruct images of acceptable quality, but it still has a lot of noise. Another issue is that FireNet Plus and E2VID Plus are sensitive to street lights at night, creating black trails behind them. We should keep in mind that Sparse-E2VID has only 0.3% of the parameters of E2VID and is 85% faster. To conclude, in this work, we introduce Sparse-E2VID, a fully convolutional model that leverages the sparse features of event cameras to reduce computational cost and inference time. Moreover, by adding real event camera noise to the training sequences, the model produces almost noise-free video. We hope that our architecture and our noise augmentation technique will inspire future research. Thank you for your attention.